We'll get started now. We're going to talk about Cryptography 101, and I'm more interested that you understand the concepts of cryptography. I'm going to happen to show it in .NET Core and C#. I have provided the slides, and I have the code in both in .NET Core and .NET Full Framework. But just be aware the concepts will apply across all sorts of languages and frameworks. Most frameworks and languages have access to cryptography libraries, so the same concept should translate pretty well. Quick shout out to our sponsors who make the conference possible. A little background on myself. I won't go through this in detail, but I have my Twitter, my email, and blog information if you want to reach out to me with any questions about the talk. So we'll get into the background. Cryptography is the science of keeping messages secure. And when people think about cryptography, they generally gravitate towards confidentiality. So most people, if you say cryptography, they're thinking about protecting the data from being read. They have a secret they don't want somebody to be able to see. That's confidentiality. It's also used for integrity. And that is where we want to verify that data was not modified, and we'll see some uses for that. It's also used for authentication, so we want to be able to identify and validate a user. And it's also used for non-repudiation, which just means if I were to send something, I could not deny later that I sent a message. So that will get into digital signatures, which we'll talk about. Within .NET, it uses system.security.cryptography. That's the namespace where you'll find all of these classes. There's a lot of considerations that go into using cryptography. So again, what is your goal? I'm going to tie back algorithms and classes throughout the talk back to your goals. Are you looking for confidentiality, integrity? So it's important that you understand which one so you are using the right tool. How much is your data worth? How long does it need to be secured? It's important to know your primary threats. So I work on an e-commerce site. I have a web server that sits on the public internet. I have to treat that web server like it's compromisable. So on any given day, somebody might find a new threat for my web server and be able to take complete ownership of my web server and all the sites on it. So I need to think about all the threats that represents and what my options are. So I'm worried about data in transit. So obviously I use HTTPS. That's keeping the traffic between the browser and the server secure. I'm concerned people could access my configuration files. It's possible if somebody owned my server that they could actually take a dump of the physical memory. So they would be able to, anything that happened to be stored in .NET, but not yet garbage collected. So if I happen to have passwords or credit cards or anything that has yet to be garbage collected, that would be in a dump of memory. So I have to consider that. Someone could modify pages. They could reverse engineer my assemblies. So I use C#. That gets built into intermediate language in DLLs. I can use ILDASM and reverse that assembly and be able to get back to pseudo source code. So if I have secrets stored directly in strings in my assembly, someone would be able to view that if they gained access to those assemblies on my server. I have company security policies I need to comply with. I have regulatory compliance like PCI. And I also want to get layered defenses. I want to have more than one thing to deter an attacker. And the question for me is, how many are going to be enough? How many layers do I need? If you don't take anything else away from this talk, don't try to write your own cryptography. So I've met several people that say, I know I'm going to write my own algorithm. It will be a secret, so that will help me with security. You know, security by obscurity. People won't know what I'm doing. History has proven that that doesn't work out well. So don't try to write your own cryptography. There are well-tested libraries available. Use those. I'll speak briefly about .NET. I wanted to mention that you'll see some suffixes used. If you ever see a class, like I'm going to talk about AES encryption, there are different suffixes which represent different things. So if you see AES managed, that means it's all written in a managed language like C#. If it ends in CNG, that means it's a wrapper for the cryptography next generation on newer Windows. And if it ended in crypto service provider, that would mean it wraps crypto API, which is available in older versions of Windows. So just so you know, in .NET Framework, what you choose for this matters depending on where you're going to deploy. It turns out in .NET Core, they took all of those classes and wrote them all to just wrap whatever library you're on. So if you're familiar with .NET Core, .NET allows you to run now on Windows, Mac, and Linux. And essentially all of these classes have been changed. They all just wrap operating system libraries now. Because of that, I also gave a link at the bottom. Not all classes are available on all platforms. So once you choose a class you want to use, generally good availability on Windows. You just want to make sure that same class is available if you're deploying to Linux. Make sure that that's going to be there for .NET Core when you go to deploy. So we'll jump right in with hash functions. So hash functions are a one-way function. They're easy to compute, but very hard, hopefully impossible to reverse. So I've got a string on the left-hand side. When I run a hash on it, it will convert that variable length data into a fixed length. So no matter what size my input data is, the hash algorithm I pick is going to dictate how large the hash is. People like to call it a data fingerprint or a digest. This hash represents everything about what's on the left. If I were to change a single character on the left-hand side, I should get a drastically different hash if I'm using a good hash algorithm. We're going to use this for integrity and authentication with some examples I'll show. There are a number of hash algorithms built into .NET. The base class, abstract base class, is called hash algorithm. Here are a number, you've probably seen some of these before. I listed the ones that are in .NET, but I put a strike through with ones that are no longer secure. So if you follow Troy Hunt, have been pwned, a lot of the data breaches that happen, people are storing passwords using MD5 hashes. That takes seconds on modern hardware to be able to attack, so it's not considered secure anymore. Same with SHA-1 algorithm. That's just not considered secure anymore. In fact, PCI regulations a few years ago said you can't use SHA-1 anymore. We use SHA-2, and SHA-2 has a number of different sizes. So these just dictate the size in bits. SHA-2 is still considered secure. There is actually a SHA-3 family. So once SHA-1 was broken, NIST, which is the standard organization working on cryptographic algorithms, had a contest for SHA-3. They did pick a winner. However, .NET does not currently have a SHA-3 implementation. From a company policy standpoint, I'm not going to use a third-party implementation, so I didn't list SHA-3 on here, but be aware there are other algorithms you could get third parties for. I'm just listing out the ones that are standard in .NET. I'm also going to talk about keyed hash algorithms. So these not only take the data you want to hash, but also use a secret key, and we'll see why those are important. And again, this is just a subset of the classes that are available. So let's take a look at how some simple hashing might work. Again, this is .NET Core. This happens to use Razor pages. I'm not going to spend time on all of that. Again, you'll have access to all of the code. You'll see I have some plain text here that I want to compute a hash of. It's very simple in .NET. I'm going to use the SHA-2 family. I'm going to use SHA-512. I just tell it to create an object. So now I have a hashing object. One thing you'll notice when you get into .NET cryptography, everything is based on byte arrays, not strings. So I need to be able to take my string, which is what all of us use, and convert it into a byte array. So there are a number of ways to do that. There's a number of encodings. I happen to use UTF-8 for this. There are other popular encodings. It doesn't really matter what you pick as long as you're not working with a partner. So in the case of what I'm doing here with hashing, I'm choosing UTF-8 because I'm only using it for myself. So I'll use UTF-8 encoding. I'll call get bytes. That takes my string, converts it into a byte array, which is what is needed by compute hash. Then I get the result, which is a byte array that is the hash representation of that. So if we were to look at what the code looks like, if I run it, there's my plain text. that's what it happens to hash to with SHA-512. So if I go back to the code, I have a byte array again. I want to be able to show that on the screen. There's a number of different ways to do that. There happens to be in .NET a bit converter class that will take a byte array and it breaks each byte up and represents it in hex, which I show here. And then I just decided to replace the dashes. And so that's how I got this value here. If I were to uncomment this really long string and recompute it, it's going to have a different hash value, but again, the size will be the same. So the size is dictated by me using SHA-512. So that's a very simple hash. Let's look at where I would use this. So one good example, you've probably seen this before. You visit a website and you notice that it has customer number on the URL, so customer number 123. If you were to go onto that URL and change it to 124, we're developers, probably using relational databases with sequential keys. If I can type 124 for customer number and see another customer's data, that's a huge problem, right? So the idea with this tamper-proof query strings is I'm going to use hashing because I want to protect the integrity of my query string. I want to make sure that you can't go on the URL and attack it and change it and be able to do anything. So let's look at what an example of that would look like. So I have a page here. It has a link. If I click that, you'll see I've got a URL here. Query string of A equals 1, B equals 2, C equals 3. Again, I don't care if people see this. It's not confidentiality that I'm concerned of, but I don't want you to be able to change this to A equals 2 and hit enter and be able to see somebody else's data. Obviously, a lot of stuff I do in here is for demo purposes. I would never show this sort of error message in production. I'm doing that so you can see what's wrong. But you can see the query string hash values don't match. So on the end, if you noticed it, I computed the value of the hash of that query string and attached it. So if you think like an attacker, maybe they would come up and try to delete the hash. That's not going to work. Let's look what the code would look like, then we'll talk about some other possible attacks and how we stop it. So here's the code. I want the query string A equals 1, B equals 2, C equals 3. I wrote a common function. I'm just going to pass. We'll go to look at that. Looks very similar to what we have before. I'm creating a hash, computing the hash, doing the string to byte. So everything here looks pretty typical. I also showed how you can use base 64 as an output if you'd like. So if I'm an attacker and I came and looked at this page and noticed that you were using a hash, I could, we won't show the whole demo here, but I would create my own page that does computing of hash just like you do, right? I mean, I have access to SHA-512. It's built into .NET. I would be able to attack you. Why doesn't that work in this case? It doesn't work in this case because I'm actually using a keyed hash. So I pass in this secret key along with the data that I want to hash, and that makes the hash turn out to be unique. So now if you think from an attacker standpoint, if they came here and tried to figure out how to break my algorithm, not only would they have to know which algorithm I'm using, they would have to gain access to my key. And again, for demo purposes, I put the key right here. Key storage is a major topic. We'll talk about it briefly towards the end. It's actually the worst thing about cryptography is how do you store keys on a server that I told you could be owned, right? But it adds one more layer. It's harder for a hacker to gain access to this than to not use a key at all. So that's a good example of where I could use hashing, get integrity, and do something practical with it on a website. Another place hashing is used a lot is for passwords. So I did security research in college and worked on password cracking and making passwords more secure. Back then it was pretty typical, about 60 to 80% of all the passwords on the Unix systems that were common at that time were from the dictionary. When Unix was created, they were trying to decide how should we store passwords, right? They thought hashing's cool. If we hashed your passwords, you type in your password, they hash it. Since you can't reverse a hash, their logic was we can store that hash password in a file. They got a little overconfident, a little complacent. They put that file in a read-only file. So anyone who had an account on Unix could go to etc password. They could see every username on the system, and they could see the hash of everyone's passwords. Again, they felt, they could use it for authentication. They thought it was great because you couldn't reverse it. The problem was people that are attacking it, if you think like an attacker, they don't try to reverse your hash. They said, well, we know most passwords are just dictionary words. They would actually pre-hash every word in the dictionary. Then all they need to do is go compare their hashed values against the actual password. So let's pull up. So I gave you an example here. Let's say this was the hash I found in the password file. All I need to do is pre-compute a bunch of words that I think might be. So here's where I'd have a loop and I'd be going through the whole dictionary. Thank you everybody on social media today as well. I would hit your Facebook, Twitter. I'd go to find anything I can about you, spouse's wife, dog, whatever, right? I'm going to hash all of those names. And then all I need to do is test this hash password against my pre-computed list. And if I were to run that in this case, we'll find out that it's actually secret. That was the password. So I wasn't able to reverse the hash, but because they weren't thinking like an attacker, they had an attack vector that allowed basically 60 or 80% of the passwords to be cracked. If you think about the good versus the bad, the good team decided, I'm going to add a salt. So they said, let's add some random data to each password. So for each user, they would pre-create some random data called salt. When you typed in your password, they would use your specific salt, and they would take that with your password, hash the two of them together, and then store that in the password file. They'd also put the salt in the password file because they need it the next time you come. They needed to know which salt they used. The good news is it made it really hard for me as an attacker. Now I can't just pre-compute every word in the dictionary. I have to pre-compute every word in the dictionary along with your salt. So it made it harder to attack the whole file at once. It just made it more computations for me. But if you think about it, it didn't help an individual password. So if I'm an attacker, I would go and find the admin user ID and try to work on their password first. Because if I were to get that, I would have the whole system. So again, it made it better. It didn't make it perfect. So if we look at the code example of how you could do this, you can generate some salt. I will deviate here for a moment. If you know, computers aren't good at random numbers, right? Computers are good at following a specific set of instructions. If you're ever going to use random things for cryptography, you have to use what's called a cryptographically strong random number generator. So this is the one that's available in .NET. It's called Pseudorandom, or it is cryptographically strong. It's much better than the normal functions, but a computer cannot ever be completely random. If you're familiar with Cloudflare, so they host a lot of internet websites and such, they wanted to get some more randomness. They have a wall of lava lamps somewhere in California they take a picture of whenever they need random data, and they use the randomness from where all the lava is to actually make some of their randomness. So side comment there, but just be aware you need to use cryptographically strong. So I generated some salt, and now I just take your data along with that salt and do the hash. They got attacked again, right? I said it didn't help protect the admin password, so they started adding in secrets too. So if you notice here again, I have a secret random data stored in my page. I'm going to use that and your salt and your password. So now if an attacker comes, they can't just take the salt and pre-compute everything. They also have to take over my machine and figure out what my secret is. So again, it's just a set of layers to make it harder. So what do people actually do today for passwords? They've been using things like bcrypt, or in .NET, there's pbkdf2. These are actually, this happens to be a password-based key derivation function you can also use for hashing. And what it does is it adds a work factor. So we'll just look at the code here. So it computes a hash. So I'm a Led Zeppelin fan, so I wouldn't actually use that for a password. But so that's my password. Here's some salt. I'm going to use this class in .NET that does the PBK DF2. The thing that's interesting is this iteration count. What you're trying to do with functions like this is make them intentionally slow. So by making it slow, I'll put in maybe 100,000. Maybe that makes it take half a second to compute a single hash. The good news is then it's very difficult for an attacker to pre-compute every word in the dictionary. If every time they try to run that, it takes half a second. They need a lot of computing power to be able to set up their attack table. So you can play with this number. You don't want to make it too big because when your customer comes back and wants to log in, you need to hash their password using this same thing with the same work factor. So you need to get a trade-off of how slow are you willing to make it for your customers while still making it hard for the attackers. But this is what people use today to be able to store passwords more securely. So that was hashing. I showed you a couple examples, one giving us integrity, one giving us authentication. Now I'm going to get into what most people think of with cryptography, which is the confidentiality, and I want to talk about a few terms. So the standard industry terms are plain text is your original data. Encryption is the process I use to obscure your data. Ciphertext is the encrypted data. Decryption is the process to go back to your plain text. The cipher is the algorithm you use. And the first type of algorithm we're going to look at is called symmetric. So when people think about encryption, this is also the first thing they think about. So we'll look at the diagram first. I have some plain text. I want to encrypt it into ciphertext. It's going to use a secret key. In symmetric, decryption uses that same secret key to get back to the original plain text. So that's how a symmetric algorithm works. Its primary attack for this, people will try to guess your secret key. If you're using a good algorithm, they're not going to break the algorithm. They're just going to try every possible key. So the good news is this is super fast and it's easy. The problem is it's hard to give out keys. And we'll talk about that a bit when we get into asymmetric. There's a lot of classes that do symmetric algorithms. DES has been around forever. It's not considered secure now. The main one you'll typically see is called AES, Advanced Encryption Standard. And this is US government sanctioned. They had a contest again. Raindahl was the algorithm that won. So I'm going to show you examples of that. So symmetric in .NET, I'm going to focus on the ones that are called block ciphers. So if I have a message, I'm going to choose a block size. So if I have a certain size message and I have a block size of 256 bits, it's going to take my plain text and break it into blocks of that size. And it's going to encrypt each block one at a time. That's just how the algorithms work. If you think about it, eventually when I get to the end of my message, it's not just going to magically fit in that last 256 bits. Some of the bits are going to be left. And so there's something called padding, and that just chooses how you fill in those last bits. I'm going to focus on the last one there, ISO. That just fills it with random data. We'll see why that's important. There's a lot of different modes you can use for AES. I'll show you ECB. ECB, the way it works, it just encrypts your first block, sets it aside, encrypts your second block, sets it aside. I'll show you why you don't want to use that. You want to use CBC. So CBC says I'll encrypt the first block. I'll take the result of that and use it as input to the algorithm when I encrypt the second block. So it adds some randomness into the next block's encryption. And again, we'll see why that's important. When we do CBC, you start to wonder, well, if you need random data as seed for your block, what do you use for the first block? And that's what's called an initialization vector. It's just random data used to seed the first block in the encryption algorithm. It does not need to be secret. I'm not a cryptographer. I've looked that up many times and I always thought, well, why wouldn't that be something that would be a secret? It does not need to be a secret for AES to guarantee security. The important part is you never reuse it. You want a unique IV every time you do an encryption. So let's look at how symmetric, well, we'll look at what it'll do first. So I will just type test. And you'll see every time I encrypt, even though this is the same plain text, you'll notice the ciphertext changes. Why is that? Because every time I'm using a unique initialization vector. And that's important because if I didn't do that, we'll see the repercussions. If I decrypt, I get back to where I started. So how does this work? So when I hit the button, I'm just calling this common method I have called create cipher. Again, I'm using .NET Core, so I won't use these suffixes. I'm just going to use the main AES class. I set the padding as I specified. Here's my symmetric secret key. I did give you code on how to create that. If you go into and run get bytes, it's just going to create a random key for you. Again, wouldn't typically store it here in the page, but we're doing that for the demo. Once I have a cipher, as soon as I create that cipher object, it created a unique initialization vector for me. I base 64 encoded it because it's a byte array. I wanted it to be in a string, and instead of, to show you, people do use base 64 a lot. That way I could display it on the screen. Then I just do create an encryptor. I will get the bytes. So I took the plain text string again, converted it into a byte array. Here's the actual line that does the encryption. And then I base 64 the result so I can show it on the page. So the important thing when you look at this, it's very serious cryptography. It's been well vetted. AES is a solid algorithm. There's not really a lot of code involved to be able to do encryption correctly. So again, this is why you don't write your own. This stuff has been looked at, vetted. A lot of people use it. It's been security tested, and it's not a lot of code if you're using it correctly. So let me go back and show how you might use it incorrectly. If I use the other padding mode and the other mode of the algorithm, I'm just going to rebuild that quick. So I switched it to ECB and 0 padding, and we'll see why this is not a good idea. So again, thinking like an attacker, I don't want to have this happen when I use these modes. So I'm going to start up my web server again. I'm going to go request that page again. And watch, every time I hit encrypt, what do you notice? The ciphertext is not changing. That's a problem, right? If I sent the same message to you every day, yes or no, right? Buy the stock or don't. You don't know which one is yes or no necessarily, but it's always going to be one of two values. That's what you don't want. I mean, people break cryptography when they see patterns all the same all the time. So that's why just don't ever use that mode that we talked about there. Use the ones that I have here on the slide. So symmetric is cool. It's really fast. The problem is key distribution. So if I picked one of you out of the chat and said, I want to send you a secret today, how would I do that, right? I see you in chat. How would I be able to communicate with you? I've got this secret, but in order to send to you using symmetric, I need to send you a secret key. It's kind of a chicken and egg. I can't send you something securely. That's where asymmetric comes in. So the idea with asymmetric is each person will create their own public and private key pair. So if I pick someone out of the chat, I would get their public key. I would take my plain text. I would encrypt it using their public key. I have ciphertext. As soon as I do that, no one can decrypt that, including me. The only person who can decrypt that ciphertext is the person who has the corresponding private key. So obviously the person I'm sending to, you never want your private key to be exposed. You want people to trust your public key, and they're able to get back to the original plain text. So again, this is great because it gets away from the key distribution problem. There's always a catch, right? The catch is it's about 1,000 times slower than a symmetric algorithm, and it also can't process a lot of data. There's a couple different classes in here. We're going to focus on RSA, which is historically used a lot. We'll go back to asymmetric here. It'll look somewhat similar. I'll type HDC, hit encrypt. I'll decrypt, get back where I was. Let's look at what that code would look like. So again, I wrote a common method to create a cipher. In this case, I just took the receiver's public key and put it in a string. So I just create RSA, I read in their public key, and then I'm going to do the encryption. So this should look familiar. I need to convert the plain text into a byte array. I do the encryption. Notice that RSA also does padding. This is the padding you want. PKS or PKCS1 is not considered secure anymore. I'll base 64 to show the result. And then you can look at the decryptions, basically the reverse of that. So again, if you look at this, it's very straightforward to use. Not a lot of code at all to use RSA, get around the key distribution problem somewhat, right? I need to get your public key in a way that I would trust. So some people put it in email signatures. I wouldn't trust that because email can be modified. Maybe you put it on your LinkedIn profile. If LinkedIn uses HTTPS, I've got pretty good confidence that's your key. If we're chatting here and I pick one of the participants, if you put your public key into the chat, I would believe that's you. We were just talking about wanting to talk. I doubt someone in the 5 seconds we were waiting intercepted, hacked your account, and put in a different public key. But that's the only thing you really need to worry about with this. So that's asymmetric. So where would I use asymmetric? So I talked about my web server could get owned by somebody. So if you think about if I took a credit card and I want to encrypt it, I don't really want to use symmetric and have to store a secret key. Because if I store a secret key like I did in my code for symmetric right in my assembly, somebody who owned my web server could take my assembly, reverse engineer it, and have my secret key. Instead, what I'll do is create an RSA key pair. I'll put the public key on my web server and keep the private key inside my firewall on the one machine that needs to talk to the credit card processor. That's the only machine that could decrypt it then. So no matter where I stored it, nobody else could decrypt it. So let's look at an example of how that would work. So here I have I've got this password number. So I've now encrypted it. The only thing on the web server is the public key. Let's say maybe I store that in a database. I go to my internal system, right, somewhere behind the firewall that has the private key and can do the decryption and get back to what we'd started with. So that is a good idea and gets around key storage problem. Today, a lot of credit card processors actually will generate a public-private key for you and not even give you the private. They'll give you the public. So as soon as your web server takes it, you encrypt it with asymmetric. From that point forward, nobody in your own company can decrypt that credit card. The only person who can do it is your actual credit card processor because they're the only one who has that private key. So now that we've talked about all of this, we'll get to digital signatures. And the idea again with digital signatures is that you want integrity and you want non-repudiation. So I want to enter into a contract with you over the internet. You want to know that when I send you the contract, it hasn't been tampered with and that you can prove I'm the one who signed it. So we'll look at how that works. Normally, digital signatures does not care about confidentiality, but for this demo, I decided to just do everything we've talked about so far. So let's look at the diagram first. I'm going to encrypt the data. So I'm going to get the receiver's public key. Whoever I'm sending to will securely get me their public key, right? It's got to be something I'm going to trust. I will take the plain text and encrypt it with their public key. I have ciphertext now. As soon as I do that, it's now confidential. No one can read it. I will compute a hash of that ciphertext and get a hash value. The way a digital signature works is I will use my private key and encrypt the hash. That's what becomes my signature. Because when the receiver gets it, they will be able to use my public key and know that I'm the only one who could have signed it. So the only way this gets broken is if someone steals my private key, they could act like me for digital signatures, which is why I need to keep that a secret. But once I do all of this, I'll have ciphertext, my contract, I'll have a digital signature. So we'll look quickly at the code for how that would work. So let's just say I'm using this to send data to a partner here. So I sent them a secret message. It was encrypted. You can see up here on the URL, I've got a secret. If I go over on the URL, you'll see I'm sending a signature. So let's look how that code works. I've got the receiver's public key. I have my sender's, that should actually say private key. I take my, oops, sorry, I'm doing the wrong one. I'm the sender. That's why that was saying that. I take the receiver's public key and my private key. And then I do things you've already seen, right? I'll create my RSA cipher. I'll read in my sender key. I will take the receiver cipher and read in the receiver's public key. And then these steps you've seen before. Here's my secret, convert it into a byte array, do the encryption with the receivers. That's what we saw with asymmetric. We do hashing like you've seen before. I compute the hash. The new part now is this signature. I will sign that now. I'm telling it I'm using SHA-512, and I create a signature that uses my private key, and then I just base 64 it. I URL encode it in this case because I put it on the URL line, and I'm done. So again, if you just take a brief look at the code, that's not a lot of code to accomplish everything we just said. I sent you something no one could read that you could prove was not tampered with, and you could also prove that I was the person who sent it. So very powerful cryptography without a lot of work. Another place you'll see all this come together, I talked about HTTPS. If you're not using this for your website, you should. Even if you only have a static website, if you don't believe that, go watch Troy Hunt has a great video on someone had a static site that he didn't think he needed HTTPS for and told Troy that he could show him why he needed it, and Troy did in very humorous fashion. So, but the idea with HTTPS is I'm a website provider. I'm going to get what's called a certificate. So my certificate is really just my server's public key that's digitally signed by a certificate authority. So a certificate authority like Let's Encrypt. If I want to create a website and use HTTPS, I'll create a public-private key pair. I'll take my public key and give it to Let's Encrypt. They will validate that I own that web server, and then they will do a digital signature of my public key. When a browser comes to my website, browsers have a built-in set of well-known certificate authorities. So they will come get the certificate. They'll see it's Let's Encrypt. They know Let's Encrypt's public key, so they can prove that they signed it. Once they believe it hasn't been tampered with and it was signed by a well-known certificate authority, they pull out my public key. They don't want to use my public key to do the actual encryption because we know that asymmetric is too slow. So the browser will get my server certificate. Browser will choose a symmetric key to do the actual encryption. It will use my server's public key to encrypt that symmetric key and send it to the server. So now this server and browser have essentially used asymmetric, the digital signatures. They've created a symmetric key that they can agree on that was transferred securely between them. Now they can do the rest of the TLS and HTTPS, and everything will be encrypted. Briefly talk about key sizes. So there are different sizes. So AES has different sizes. You could use 128-bit or 256-bit keys. I talked about people who break AES or have to brute force try every single key. It's not twice as hard to try 256 bits compared to 128. It's exponentially harder. So because I'm not going to get fired over the millisecond difference possible with using a slightly larger key, I'm going to use the largest key sizes that are possible because I'm worried about the security. If you're not convinced and worried about it, I've run the test. The difference in how for performance you'll never notice. It's not worth cheaping out on your key size. We talked about key storage. Like I said, this is by far the worst part of cryptography, right? I have a public web server that I think somebody could take over. How can I possibly store something securely on it? That's a major problem. I got around it by not trying to store secrets there, right? I'm going to use a public key on there. That way I don't have to worry that someone will steal it. If I do have to store a secret for some reason, like for hashing or such, there's all sorts of options depending on your environment. Azure Key Vaults, you can use layers, you can split it in code registry. So I don't have enough time to go into all of this. To just suffice to say, this is the worst part of cryptography in my mind. So the summary again, don't write your own cryptography. Use trusted algorithms and implementations. Know what you're trying to do. If you're trying to validate integrity of data, use hashing. Use symmetric algorithms because they're so much faster unless you have a special need for asymmetric, like you have a key exchange problem or you need to do digital signatures. And think through your threats and make sure you're choosing the proper countermeasures. So know your environment and think about how you might be attacked so you can make sure that you're covered. I have a Pluralsight course, goes into a lot more detail about this in .NET framework in that case. There's some good books if you like to know exactly how AES is implemented, all the bit shifting and that, these are good books. I don't care about the bit shifting and how the algorithm actually works. I still read these because they explain how to use AES in addition to exactly how AES works. If you're interested more in the history of cryptography, the Caesar cipher, the Vignette cipher, Cytales, how it all started, and the arms race between good and bad, these last two books are very good, detailed books, just with a lot of history of how people broke algorithms and such. That is my Twitter, my email, my blog. The slides and the code were uploaded to the conference site. I also have a link there if you want access to the slides and the code. If you do have any questions, feel free to follow up with me afterwards on Twitter or email. And please do the session evals for me, please. I would appreciate knowing how everything has gone. And lastly, let me go see if there's any quick questions here that anybody had. Okay, I don't see anything in particular. If there was one I missed, if you want to retype it quick. Otherwise, like I said, I will put up my slides here again at the end. Are there any hardware-based key stores for personal use? I haven't used them, but like YubiKey and some of those are hardware-based, like USB typically, that will store your keys for personal use that you can put into the USB as you need to access that key store. Makes sense for personal use. You know, most of what I've been talking about is more for server usage and places where that wouldn't make sense, but I haven't used any myself, but like YubiKey I know is one of them, and there's one from Google as well. All right, I'll just put this back up in case you want access to the slides and the code. And that is all that I had. So thank you for coming.